Those who are online are able to hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. See, when I share the screen, right, is it appearing big or small?
Big only, sir.
Big only, sir.
Okay, perfect. This one. Now it's big enough, right?
Yes, sir.
Okay. Done. Yeah. So what was I asking? Yeah. Any doubt from the concepts that we have discussed? Is everything clear? Oh. So yeah, can we? Yeah, tell me. After the class, I'll explain. Math. No? Which one? Gauss law. No need. We will not use it anyway. Okay. So tell me. Any doubt? So you understood the concept of charge distribution, right? So there are three types of charge distribution. What are they? Linear, surface, and the volume charge distribution. So with the help of those charge distributions, what we are going to do is, right? So what we are going to do is understand this Gauss law. See, for example, let's say I have a system where it's a linear charge. So due to the linear charge distribution, if I'm interested to calculate the value of electric field, let's say at a distance r from the point P. Okay. Then see, if I need to use Coulomb's law, then what should I do? Will I be able to use Coulomb's law in the first place? Maybe I can, if I'm able to break it into infinite number of point charges, right? So what I need to do is I need to take a small point charge dq, and due to this dq, what will I do? I will find the electric field due to this at this point, right, which is going to be dE. I'll find this value and then integrate it, which is a tedious process. Right? You can do it, right? You will get an answer, but it will be slightly difficult. So what has happened is, in order to solve this issue, right, of this extended charge and the concept of symmetry, there is an other law which is going to help us to solve the problems, and that is what this Gauss law is. So if we need to apply this Gauss law, see, it's very simple. Okay, if I ask you, if you look at a question, when are you going to apply Coulomb's law? Like, the question itself will give you a hint. Okay, this problem I can solve it using Coulomb's law. What does it state? First thing, it should speak about 2 point charges or more than 2 point charges, and if you know the distance of separation between them, you're clear that yes, I can solve this problem using Coulomb's law, right? Whereas, when will you know that, okay, I can think of Gauss law? Is a question, right? So Gauss law is a law which relates two important concepts. One is the total electric flux. So in the previous class, I discussed about flux. No? So what is flux? Flux is the total number of field lines that are passing through a given area perpendicular to it, right? So if I know the flux that is getting generated due to a charge distribution, and if I know the total charge which is present within the closed surface, if I am able to relate these two concepts, then I can apply Gauss law. So what is the hint again? I come again. What is the hint? When will you know you need to apply Gauss law? Gauss law is the law that relates the flux through any closed surface and the net charge that is enclosed within the surface. Right. So if I have the concept of electric flux and the total charge that is known to me, I can solve that problem using this law. Is that clear? So that is the first part. Okay, it relates, but how does it relate is what the statement is. So the statement says, if you know the total flux generated due to the electric field, right? So the total flux that is generated due to the electric field will be equal to 1 divided by epsilon naught. 1 divided by epsilon naught. What is epsilon naught? Is the permittivity of free space. 1 divided by epsilon naught times the charge that is present within the closed surface. So for you to define flux, what is it you need? You need a closed surface in the first place. right? So what are they saying? You can always relate the total flux that is coming out of or going into a closed surface is equal to 1 by epsilon naught times the total charge that is enclosed within the surface. So that's what the statement is. But how do I write it mathematically? So I need to convert the statement into a mathematical part. So phi stands for flux. So if I put a subscript E, then this will be equal to 1 divided by epsilon naught times the charge that is enclosed. ENC stands for enclosed. Okay, it's a subscript. So the electric flux is equal to 1 by epsilon naught times the charge enclosed by the closed surface. I'll tell the name of the closed surface, right? This is one point. Or this flux is there, no? You can write the flux in terms of electric field and areal vector. How do you write it? Or you write E vector dot A vector is equal to 1 by epsilon naught times the charge enclosed by the Gaussian surface. That is one thing. And the next important thing is, not every time you will know the exact value of electric field and the exact value of areal vector. Sometimes you will be able to know only the value of small dA, small areal vector, that is dA. At that time, what you're supposed to do is, you'll write it like this: E vector dot dA vector is equal to 1 by epsilon naught times the charge enclosed by the Gaussian surface. Listen to this carefully. This is only the flux through the small area dA, right? If I put an integral symbol like this and put a circle around this, you will call it as surface integral of E vector dot dA vector is 1 by epsilon naught times charge enclosed. So how do you read this as? You call it as surface integral. So surface integral of E vector dot dA vector is equal to 1 by epsilon naught times the charge enclosed by the Gaussian surface. Okay. So these are the three ways in which you can mathematically write, but there is the definition. Please make a note of it. You call it a surface integral of E vector dot dA vector is equal to. I'll explain what that surface integral is when we solve. Done? Shall I proceed?
Yes, sir.
Yeah. So we were saying or speaking about something called as a closed surface. No, the closed surface has a name, which is called as the Gaussian surface. So what does this Gaussian surface speak is? It is basically a closed imaginary surface. It's an imaginary one. It's a closed imaginary surface, right? And it's a three-dimensional figure. So the closed surface which we consider around the charge distribution will always be a three-dimensional figure. And the most important point which I wanted to state here is, whenever you are applying this concept of Gauss law, it depends only on the charge that is enclosed within the surface. Right? It depends only on the total charge that is enclosed within the surface. So that's what they're saying. See, Gauss law tells us that the flux through any closed surface S depends only on whom? Only on the value of the net charge that is present inside the surface, and it does not depend on the location of charges at all. So if you take a Gaussian surface, inside the Gaussian surface, if you know what is the value of net charge that is present, that is more than sufficient for you to apply this Gauss law. Okay, let me take an example and explain it. Suppose I have a surface like this, Gaussian surface like this. If I take this to be the positive charge, okay, and let's say this value is Q, right? Now, due to this, how is the electric field going to be? It is going to be in the radially outward direction. Right. If you ask you what is going to be the flux through this, what will you write it as? Flux through this is 1 by epsilon naught times the total charge that is present within the surface, which is Q. Done. This is what Gauss law says. Okay. Now I have a question. If I take this radius to be R, if I increase the radius from R to 2R, then what is going to be the value of flux? If I increase the radius from R to 2R, right, then what is going to be the, sorry? So what should be the value of flux? It should be the same value, right? It is Q divided by epsilon naught. One major confusion that happens here is people start connecting it with E dot A, electric field into area. No, since the area is increasing, they will think flux is also increasing, but nothing will happen, because what does Gauss law state? The flux through the surface depends only on the net charge that is present inside. It doesn't even depend on the location of it. When you know that the net charge present is Q, whether you take a Gaussian surface of R, 2R, 3R, 5R, whatever R, the flux value is fixed. This is a very important question. Most of the times they'll ask. Okay, this is one thing. Secondly, if I take another system like this, let's say I have charge Q1 minus Q2, Q3 present like this, right? Q4 and Q5. Okay, negative of Q5. Then what is going to be the flux through this? So flux will be equal to Q1 minus Q2 plus Q3 divided by . So another important point to be noted is the total flux depends only on the charge that is present inside the Gaussian surface. Whatever is the charge outside the Gaussian surface will not contribute to the flux at all. So that's what the second point is. Charges outside the surface will not contribute to the flux at all. And secondly, what did we do here? I didn't write it as Q1 plus Q2 plus Q3. I wrote it as Q1 minus Q2 plus Q3. What property of charge did we apply? It's additive nature of charge. So we applied the additive nature of charge. Am I clear with this? Right? So this is all about the Gaussian surface and the important points related to Gauss law. Right? So please make a note of it. Here. So let me know once you're done copying it. You're done? Please make it. You're done there? Shall I proceed? So we have learned the basics of Gauss law, right? See, those who are online, shall I proceed?
Yes, sir.
Okay.
Yes, sir.
So now we saw the basics of Gauss law, right? And we understood what are all the mathematical expressions associated. Now we need to start applying. Okay. So as I told you, these are the steps that are used in Gauss law. So this part alone, what I want you to do is keep your book horizontal and write. Okay. As of now, don't write. First listen. After I complete, write it in that form. Okay. See, what I'm going to do is, I'll tell you the steps that we need to apply, steps we need to follow to apply Gauss law. It is not applicable only for the applications that we have in this chapter. It is applicable everywhere. Any problem that is given, these are the steps. Okay. So first is define the type of charge density, meaning depending on how the charge distribution is present. Sanjay, listen. Depending on how the charge distribution is present, you need to first define the type of charge density. In the sense, if the question consists of linear charge density, if the question consists of a linear or a charge distributed on a line, you will think of linear charge density. On an area, surface charge density, volume charge density. That is the meaning of the first step. Second, we need to consider a Gaussian surface around the charge distribution. Right? They give you a system, right? Around the charge distribution, we need to consider a Gaussian surface. And when you consider it, you need to ensure that the Gaussian surface is always passing through the point where we need to calculate the electric field. Okay. Now, to understand this, instead of me telling all the steps in application, right, I'm going to relate a concept. Now, what is the value of electric field due to a point charge? What is the value of electric field due to a point charge at a distance r? It is going to be kq by r square. We know this and we have applied it also many times. Now, what we are going to do is this. How did we derive in the first place? Using Coulomb's law, E is equal to F by Q. Remember? So, using Coulomb's law, we derived it. Now, we'll use Gauss law and derive it. Okay. For which I'm going to take a point charge like this. First thing. Second, define the type of charge density. Here, it is a point charge. So, there is no question of charge density. Charge density is mostly used only for extended charges. So, there is no charge density. Then, let's say this is the point where we need to calculate the electric field. What is that we are supposed to do? We need to consider a Gaussian surface. We need to consider a Gaussian surface around the charge distribution. Remember, the Gaussian surface that you consider should always be symmetric with respect to the charge distribution. Meaning, if I take this to be the point charge, this P, let's say it is at a distance r. Okay, let's think of it like this. Not necessary that this P should be here only. It will be here, it can be here, it can be anywhere, but at the same distance r. So when I join all these points, all the points of P that are possible, what is the shape I'm going to get? The shape I'm going to get is going to be a circle if you take it in a 2-dimension. But the question is, when this charge is there, the point P can be here also. The point P can be on the back side also. Right? So the point P can be on the back side also. So what is the shape you are going to get? You will get a sphere. Am I clear? So you will get a sphere. I hope the second step is clear. Consider a Gaussian surface, and I followed something else also. What is that? I've considered it through the point where the electric field is to be calculated. Third step. On the Gaussian surface, consider a small area dA. So the Gaussian surface is a sphere. On that sphere, we are going to take a small area dA. Right? So let's say the area is considered like this. Right? We'll consider a small area dA, and what are we supposed to do? And assign direction to it. What is the direction of aerial vector? From the previous class, tell me. It is always in the radially outward direction. Check your notes. Direction of aerial vector when I explained the Gauss, electric flux. It is always in the outward direction, perpendicular to the surface. That is what radially outward. So here it is going to be in this direction. Am I right? So we have considered a small area dA and we assign the direction to it. The next step that we are supposed to follow is find the direction of electric field through the small area dA that we have considered in the step number 3. So due to this point charge, how is the electric field going to be? It will be away from it. Am I right? So can I say that this electric field, right? Electric field and dA, are they both in the same direction? They both are perpendicular to the surface in the outward direction, right? So find the direction of electric field through the small area dA considered in step number 3. And the fifth step is find the total charge that is present within the Gaussian surface. In this case, it's very simple. What is it? It's Q. Right? The next step is, there are 2 more steps. The next step is applying Gauss law. What is the surface integral of E dot dA is equal to Q by epsilon naught. Okay. And the last step is solve for the electric field. Okay. These are the steps to be followed. Now see, the surface integral of E vector dot dA vector is how much? The total charge that is enclosed by the Gaussian surface. How much is the charge present inside? Only one charge, Q, divided by that. Now, what is the angle between both? What is the angle between both? Electric field and dA. 0. They both are in same direction. Right? So, surface integral of, can I write it as E into dA is equal to Q divided by epsilon naught? I take the electric field outside. Why will I take the electric field outside? Because it is a constant value. Why did I say it's a constant value? Is because due to this charge distribution at a given distance, electric field is always constant. Electric field at a given distance is always a constant. So if I take this E outside, E into the surface integral of dA is equal to Q divided by epsilon naught. Now the question is, on the sphere, if you add all the values of dA, what will you get? On the sphere, if you add all the values of dA, what are we going to get? You will get the surface area of that sphere. Okay. So let me see if I'm able to explain it visually. 1 minute. See, just to be clear, I've taken a spherical balloon. right? Inside this, what you have? You have the charge q. Due to the charge q, the electric field is in the outward direction. So on this, what we did is we took a small patch, right? We took a small patch, which we called it as dA. And due to this dA, what is the direction? For this dA, what is the direction? It is a radially outward direction. What is the direction of electric field? That is also in the outward direction. So they both are in same direction. That is why we wrote E into dA. Now what we are doing is we are taking many such aluminum foils and pasting it on top of this surface of the sphere. When you place it, this aluminum is covering what area? The surface area of the sphere. So what is the value of the surface area of the sphere? So E into 4 pi r square is equal to Q divided by epsilon naught. So E will be equal to Q divided by 4 pi epsilon naught. I'll combine. R square, I'll write it separately. Is this not the value that we already know? That's what I wrote it as K. 1 by 4 pi epsilon naught is what is K. I hope it's simple, right? Right. So this is how you apply Gauss law. But we have different applications. We have 3 applications for extended charge. But I thought I'll create a similarity between the steps that I've mentioned and the point charge. Is that clear? Right. So please make a note of it. keep your book in the horizontal way. You already started writing. Done. Yeah, clear. Yeah. Shall I proceed? So there are two more steps in the next page. I hope you all wrote it. The step 6 and step 7. Right? Those who are online, are you done writing?
1 minute, sir.
Yeah, right. This page or the previous slide?
I can go to the previous slide, sir.
Yeah, 1 minute. You can just take a screenshot and maybe write it later so that we can save time. Can you?
Okay, sir.
Yeah. Take a screenshot. Oh, sorry. Take a screenshot and have it. Let me know once you're done. Shall I proceed?
Okay, sir.
So we'll see the first application due to Gauss law. Right? So since now we know the steps, so when we see the applications of Gauss law, there are three important applications. The first one is applying this for an infinitely long charged wire. Okay. So if I observe this, then I have an infinitely long charged wire, right? On which there is obviously charge that is distributed uniformly. So what do you mean by uniform distribution? Listen, if suppose I take a wire like this, 1, 2, 3, 4, for instance, there are 4 point charges summing up to give you the total charge. And let's say the length of it is, for instance, 8 units. Then what will you write the value of lambda as? Lambda will be written as 4 units divided by 8 units. So the lambda value is going to be half. See, this is only for understanding purpose, right? Suppose I break it into 2 charges. right? If suppose I break it into 2, if I write 2 in the numerator, what should be in the denominator? I should have a 4 in the denominator so that I have the same half for the lambda. That is the meaning of uniform distribution of charge. Am I clear with this? Okay. So you have a system of this format. For which we are going to calculate the value of electric field at a distance r from it. So if I take a point P, which is at a distance r from it, right? Now, first thing is, we need to define the type of charge density. What is the type of charge density we can define here? Linear charge density. The first step says purely lambda, right? Second step, it says we need to consider a Gaussian surface around this. So the Gaussian surface is supposed to be symmetric with respect to the charge distribution. Okay, listen to this carefully. If this point P is here, the point P can be here, it can be here, it can be here, it keeps on going like this, right? So when you join all these points, you get a straight line. Similarly, this point P could have been on the other side at the same distance R. That is another straight line, right? But at the same time, this point P could have been here. It could have been here in the space. It can be anywhere. So when you join all those points, then the shape that you are going to get is going to be a cylinder. So this is going to be the Gaussian surface. And we also ensured that the Gaussian surface is passing through the point where we are interested to calculate the field. Next step. On this Gaussian surface, we need to consider a small area dA. So if I take the area to be dA like this, see, for example, let's take this water bottle, assuming it to be cylindrical, okay? If I take this to be dA, then this dA is over here. Then for this dA, right, for this dA that I've considered, what is the direction of what is the direction of aerial vector? This is the direction. It's radially outward. So I've taken this dA in this direction, right? So consider dA and take the direction. What is the fourth step? Direction of electric field. Since here we have a system of positive charges, due to the positive charge, what is going to be the direction of electric field? Is it away or away? So it is going to be away, again perpendicular to this. So this is going to be the direction of electric field also, right? What is the next step? Find the total charge that is present. So if I take this height to be h for the time being, right? So what is the charge density? So charge density is lambda, but we know that charge density is the charge per unit length. So what is the total charge enclosed within this Gaussian surface? See, lambda is equal to Q divided by L. So Q will be equal to lambda into L, right? So in this case, what will happen is the total charge inside the Gaussian surface is equal to how much? The linear charge density multiplied with the length of it, which is h. Am I clear with this? What is the next step? Apply Gauss law. The surface integral of E dot dA in the vector forms is equal to 1 by epsilon naught times the charge enclosed by the Gaussian surface. So I'll write this formula every time. What is the angle between electric field and dA? 0. So I can write it as E into dA. So in this case also electric field is a constant. So I can take the electric field outside. So E into the surface integral of dA is equal to, what is the charge enclosed within the Gaussian surface? It is lambda into h divided by epsilon naught. Now tell me one thing. For this surface, if I add all the dAs that are present here, what do I get? What surface area? You get the curved surface area, because if you see for the cylinder, here also you can take a Gaussian surface. Sorry. Here also you can consider a small area, meaning you can take an area here. The areal vector's direction is upward. What is the direction of electric field? Rightward. What is the angle between both? 90. So what is cos 90? Because when you're doing dot product between two perpendicular vectors is 0. Similarly, if I consider another dA at the bottom, for the bottom, the value of areal vector is in downward direction. Electric field is in this direction. So what is the angle again? 90. So through this surface and this surface, there is no contribution of flux. So the flux is contributed only through the curved surface area. So the surface integral of dA in this scenario will give you the curved surface area of a cylinder. And what is the curved surface area of a cylinder? It is 2 pi RH, which is going to be equal to lambda into h divided by epsilon naught, h and h. Right? So from here, E will be equal to lambda divided by 2 pi epsilon naught R. And this is going to be the value of electric field due to a linear charge distribution at a distance R. Right? As I told you, you can derive this thing using Coulomb's law also, but it would have taken at least some 10 to 12 steps. But here, look at the number of steps. We are able to do it faster. Right? So one thing is, this is a value. Right? Let me complete it, then you can copy. So for this value, we know that E is equal to lambda divided by 2 pi epsilon naught R. See, there is something you will not find in your textbook. If you plot the graph between electric field and distance. So tell me one thing, when I say the graph between electric field and distance, which one should I take on y-axis and which one on x-axis? Electric field on the y-axis and the distance on the x-axis. Why is it so? Because the x-axis is always independent. You're able to understand? Right? So lambda is a constant because uniform charge distribution. 2 pi epsilon naught is a constant. So E is inversely proportional to R. So it is of the form y is inversely proportional to x. So you will get a shape like this. So this is how the graph between electric field and the distance going to be for a linear charge distribution. Am I clear with this? Right? So please make a note of it. Understood? See, all these derivations are very important and you are expected to remember this result. Okay. Let me know once you're done. So copy this part and this one also. Done now? Shall I proceed? Okay. So there are two more applications. One is for an infinite plane sheet, and the next one is for a uniformly charged spherical shell. First, I'll finish this, then we can go to the next one. So now we'll find the electric field due to a uniformly charged spherical shell using Gauss law, right? So here, if you see, you have a spherical shell. Meaning of it is, it's a hollow sphere. And for a hollow sphere, remember, whatever charge you're trying to give to the system will not go and sit inside the sphere, rather it will sit on the surface. Why is it so? Because when I say hollow, there is no mass at all. Then there is no question of transfer of matter, right? Right. So for this kind of a system, we'll find it 3 points. One is inside, one is outside, and the last one is on the surface. Okay. So if I take this to be the center, from the center, first I'm taking a point inside. If I take P1 to be inside, let's say at a distance small r. Okay. So at P1, and where is that point P1 considered to be? It is inside, right? You tell me what is the kind of Gaussian surface that we are supposed to consider. So Gaussian surface should be symmetric with respect to the charge distribution. So where is the charge distributed? On the surface of the sphere. What is the symmetric shape to it? Another sphere, right? So if I take this to be the Gaussian surface, right? I've considered it through the point and everything. Here, one thing that I'm going to directly write is, I'll directly go to apply the Gauss law. So E vector dot dA vector is equal to 1 by epsilon naught times the charge enclosed by the Gaussian surface. Here, what is happening? Whatever charge you give is not sitting inside, it's sitting only on the surface. So what is the charge enclosed within? So charge enclosed is a 0. So when this is going to be 0, then the electric field will also be 0. Meaning there is no electric field present inside a spherical shell. So where does it start from? It starts only from the surface, because that is where the charge is present. Am I clear with this? Right. Now we'll do for outside point. For outside, I'll consider the point to be P2, for instance. Okay, what are the surface we can consider? With respect to the charge distribution, it's distributed on the surface. So I can consider another sphere which is concentric with respect to this. Right. Having said this, what is the next step? I need to consider an aerial vector. So what is going to be the aerial vector that I'll take? It will be dA and it is directed in this way. And what is the direction of electric field? That is also in this way. So what is the angle between both? Angle between both is 0. So for point P2, that is outside, if I directly start applying the Gauss law, then I'll get the surface integral of E vector dot dA vector is equal to 1 by epsilon naught times 1 by epsilon naught times the charge enclosed by the Gaussian surface. This is where we need to be careful. If you take this whole concentric sphere, right, what is the total charge enclosed within it? It is going to be the charge that is present on the surface of the spherical shell, which is Q itself, right? So surface integral of E dot dA can be written as E into dA will be equal to Q enclosed is going to be equal to capital Q divided by epsilon naught. So what you can do is take the E outside, which implies E into the surface integral of dA is equal to Q divided by epsilon naught. So what is going to be the value of E? What is the surface integral of dA? Let's say this radius is R. 4 pi R square will be equal to Q divided by epsilon naught. Point to be noted here is the small r is a variable. Okay. So what I'm trying to say here is I'll take the radius of the sphere to be capital R, which is fixed. Whereas small r is a variable at P1, P2, it keeps on varying. Right. So what will be the value of E? Q divided by. That's it. So this is the value of electric field at a point outside the spherical shell. If you see this outside the spherical shell, right, it is acting similar to a point charge. Meaning, for a spherical shell, if you calculate the electric field outside, it is the same as you having a point charge which is placed exactly at the center at a distance r from this point P2. Both are having same scenario. See, they both are not same, but it is acting as if it is a point charge which is placed at the center of the sphere. Am I clear with this? Now, the last one is on the surface, which is simple. So when I say on the surface, no, what I'll do is small r will be equal to how much? Small r will be equal to capital R. So small r is equal to capital R. Take this and substitute it there. What is going to be the value of electric field? E will be Q divided by 4 pi epsilon naught capital R square. Now understand this capital R square. Capital R is a constant. Small r is a variable. So is it clear till this step? Right. Having said this, if I frame a small mathematical equation, meaning if I write the value of E, E will be equal to 0 when the value of small r is less than capital R. Meaning of it, if it is inside. Am I right? It is equal to Q divided by 4 pi epsilon naught. You can observe it to be capital R square when small r is equal to capital R. This is on the surface. Then what about this? Q divided by 4 pi epsilon naught small r square when the value of small r is greater than capital R, when it is going to be outside the surface. So having said this, when you plot a graph, right, between the electric field and R, this R is there, no, till the value capital R, it will be 0. It will be 0. After that, it will reach a value which is equal to how much? Q divided by 4 pi epsilon naught capital R square. After that, what will happen is it will decrease as a function of small r square. So this is the graph for q divided by 4 pi epsilon naught small r square, and this is a very, very important graph. So I hope it is clear, right?
Yes, sir.
So make a note of it. The next slide, did you guys copy it?
Yes, sir.
This one. Done? Okay. This part, make sure you use a different color. So there is one last concept that is left out, that is electric field due to an infinite plane sheet, which I told you. See, what I'll do is that part alone I'll pre-record and send, so that we need not wait till next week. You can go through that content, prepare the notes and come. It will take only 10 to 15 minutes, so that this chapter is done. And next two classes, or at least we'll see. Next class, at least I want to solve problems based on this. Okay, as I discussed, we'll focus more on problem solving and questions related to boards. Clear? So any
Yes,
other
sir.
doubt from today's class?
No, sir.
Everything's clear?
No, sir.
Okay. So that's it from my side. I'll see you all on Monday.
Thank you, sir.
Thank you, sir.
Yeah, ma.
Thank you, sir.
Yeah.